In this lecture now we will talk about, or we'll compare the reactivity of haloarenes and haloalkanes, right, towards nucleophilic substitution, and we'll see the reason why haloarenes are less reactive towards nucleophilic substitution, right. Now let's just look at the reaction. If we try to convert a haloarene, right, this into an alcohol, right, we need drastic conditions, right. When we say we need drastic conditions, we need drastic conditions like 300 atmospheres pressure, 623 Kelvin temperature, right, to convert it into phenol. This is phenol, and this reaction is a nucleophilic substitution reaction, where this Cl, we know it's a nucleophile, it's a weak nucleophile, right, would be attacked by hydroxyl nucleophile, which is a strong nucleophile, right. So here this strong nucleophile will replace this weak nucleophile, so it's a nucleophilic substitution reaction. But you have to look at these conditions. These are very drastic conditions, right. 623 Kelvin temperature, 300 atmospheres pressure. So, but if you try to convert an alkyl halide, say ethyl chloride, into ethanol, right, then you don't need these drastic conditions. The reason being, your haloarene is less reactive towards nucleophilic substitution as compared to alkyl halides, right. We say that haloarenes are less reactive than haloalkanes towards nucleophilic substitution. Right. So these are less reactive compared to alkyl halides, or compared to haloalkanes towards nucleophilic substitution. Now we'll look into the reason. What is the reason for the less reactivity of haloarenes? Right. If we look at the structure wise some details, we know that this carbon atom is sp2 hybridized, right, and talking about methyl chloride, this carbon atom is sp3 hybridized, right. And if we look at the bond length, CCl bond length is, in haloarenes it is 1.69 angstrom, right. The bond length is 1.69 angstrom, and here it is 1.83 angstrom, right, or I think it is 1.82 angstrom. It's near, nothing, that doesn't matter. We just have to concentrate that the bond length in haloalkanes is more compared to bond length in haloarenes. We need to look at the reason why, right. And this sp3 hybridized carbon is less electronegative. We have discussed this in previous lecture also, right. And this sp2 hybridized is more electronegative, right. So these are the details, these are the structural details that you should know before going into the reason, to look into the reason why these haloarenes are less reactive than haloalkanes. We need to look at the reasons for all these. So first reason is what it means when we say these are less reactive compared to this bond. This bond is strong in haloarenes, right, compared to haloalkanes, right? Let's see why this bond is more strong bond. First is your reason is, let's look into the reason, the resonance effect, right? As per the resonance effect, this bond in haloarenes develops a partial double bond character, right? And we know that double bonds are stronger compared to single bonds, right? So as per this, the CCl bond develops partial double bond character, double bond character, that makes it a strong bond, right? This is a strong bond due to partial double bond character. Now let's see why it develops this double bond character. This is your benzene. This lone pair of benzene enters into conjugation with the benzene ring, right? This lone pair will enter into conjugation with the benzene ring, so it will start moving in the benzene ring along with the benzene ring, right? Due to which the CCl bond will develop a partial double bond character. And we know that double bonds are stronger bonds. We do need to give them more energy in order to break, right? So that is why you need these drastic conditions in case of haloarenes. And we also know that double bonds are shorter bonds, right? That is why here you see it's the length of this CCl bond is 1.69 compared to that in haloalkanes where it is 1.82. So this shorter bond is due to this resonance effect, right? Bond has become short due to this resonance effect, and this short bond is confirmed by techniques that this bond has developed a partial double bond character, and this bond length has also been confirmed by experiments, right? So let's look into the resonance forms. This electron will start moving, right? So this is how you need to draw the resonance structures. Right? So here it will develop, due to this resonance, a double bond character. This is your double bond, right? Right, so due to this double bond character, this is a stronger bond, right? Due to which its cleavage is difficult, or it is difficult to break this CCl bond because it has now developed a partial double bond character, right? So you have to give it more energy in order to break it. That is why you need drastic conditions. The second thing, if you look at the structure, this carbon atom is sp2 hybridized, right? Whereas if we talk about haloalkane, this carbon atom is sp3 hybridized, right? Now sp2 hybridized, we have discussed this one thing before, that this is your bond pair of electron. Since this Cl, right, since this Cl has high electronegativity, so it will displace this shared pair towards itself, giving it a slight negative charge. Here you have a positive charge, right? So this bond is polar, right? Due to this electronegativity difference, this bond is polar. Now this bond has become polar because this electron bond pair, the shared pair or the bond pair of electron, has moved more towards chlorinate. Now anything that will attract this shared pair towards carbon atom will decrease the polarity, right? Now less polarity means less reactivity. Since this bond is polar, that is why these halides are reactive, right? And anything that will lessen this polarity, anything that will decrease this polarity, will reduce the reactivity, right? It will reduce the reactivity. If you reducing polarity means displacing this electron back to its central position, more close to central position, right? Now this carbon in these molecules in haloarenes is sp2 hybridized. When we say sp2 hybridized, they are more electronegative. They are more electronegative compared to these carbon atoms, right? These carbon atoms in alkyl halides, these are less electronegative, right? Since this is more electronegative, this carbon atom, right, which is this carbon atom, right, which is in benzene, right, this carbon atom is sp2 hybridized, so it is sp2 hybridized, right? So it will attract this shared pair of electron more towards itself back, right? Now when it will attract this shared pair more towards itself, this bond will become less polar. So when it will move more towards carbon atom, the release of Cl will become less, right? Release of Cl will become difficult. It will become difficult, right, compared to its release in alkyl halides or in haloalkanes, right? So we say due to high electronegativity of carbon atom, because it is sp2 hybridized, the release of halogen atom in haloarenes will become difficult because this shared pair of electron would be more strongly attracted towards the carbon of the benzene ring, making this bond less polar and less reactive. Whereas if you see in haloalkanes, you have sp3 hybridized carbon atom. sp3 hybridized carbon atom is less electronegative, right? When we say less electronegative, that means it will attract this shared pair of electron less towards itself. It is still more towards Cl, right? So due to which it is more polar and release of this Cl is easier, right, in case of haloalkanes. So since release of Cl is easier, right, in case of haloalkanes, so this nucleophile, right, OH would easily replace this nucleophile in case of haloalkanes. Whereas in case of haloarenes, since the release of Cl is difficult because the electron pair has shifted towards carbon atom, or this carbon atom is attracting this shared pair towards itself strongly because of high electronegativity of carbon atom due to sp2 hybridization, release of Cl is difficult. That is why you need drastic conditions, right? I hope this is clear. So sp2 hybridization, why electronegativity is more of sp2 hybrid orbitals? If you want to look into it, sp2 hybrid orbitals, right, has more s character, right, compared to sp3 hybrid orbitals, right? This has more character. You can see this is sp3, right? So this has around 25% s character, right? And this one has around 33 or more than this percentage of s character. Basically the s character is more here, right? So since s character is more, we know that when we say s character is more, we are talking about s orbital, right? And we know that from electronic configuration, s orbitals right? We start with this, like this, 1s2, 2s2, 2p6, right? These s orbitals are closer to the nucleus in an atom, right? Since the electrons that are in s orbital are closer to the nucleus, so they are more tightly attracted by the nucleus, or more strongly they are attracted by the nucleus, the electrons in the s orbital. So more s character means the electrons in the s orbital would be more strongly attracted, right? So here also, since s character is more, so electrons, due to this more s character, this electronegativity of carbon is higher, because it is able to now attract this electron more towards itself due to higher s character, right? I hope this is clear, right? So basically we have the reasons that we need to look into is resonance effect. Due to resonance effect, a partial double bond character has been developed, right? Now a double bond, we know, is a stronger bond compared to a single bond, so that is why you need to give more energy here, right? If you compare it with this molecule, here it is a purely single bond, right? Seeing single bond is a weak bond, so you need to give it less energy, so less drastic conditions. The second is sp2 hybridization of carbon atom. Due to sp2 hybridization of carbon atom, this has high electronegativity due to high s character or more s character, and we know that electrons in s character are more tightly bounded because they are more closer to the nucleus, so electrons are more tightly attracted or more strongly attracted. So this electron pair is more strongly attracted towards this sp2 carbon of this benzene ring, right? And here sp3 hybrid carbon atom is less electronegative, right? This is less electronegative because of less s character, right? Due to which, since now due to this more s character or high electronegativity of carbon, this electron is displacing away from Cl atom, right? Chlorine atom or any halide atom. So the release of this Cl, right, would become difficult, right? And this bond is less polar compared to in haloalkanes. I hope this is clear. So your resonance effect, sp2 hybridization and polarity, right, will decrease the reactivity of CCl bond in haloarenes compared to haloalkanes. Now it is observed that if you have electron withdrawing groups in haloalkanes at ortho and para positions, right? For example, let me just rub this off. If the electron withdrawing group increases the reactivity of haloarenes towards nucleophilic substitution, right? Now let's quickly look into the reactions, right? Now if I take this, right, now in this case, if I put NO2 in para position, the condition of the reactions will change to 443 Kelvin, less temperature, right, as compared to the previous one, right? And if I put instead of 2, if I add one more, say if I add one more NO2 here, temperature will further reduce from 443 to 368 Kelvin, right? Now say if I add one more NO2, the reactivity will again increase. Lessening temperature means I'm lessening the drastic conditions because the reactivity is increasing due to the presence of NO2 group at ortho and para positions, right? So here if you have these NO2 groups at ortho and para positions, now all the ortho and para positions are occupied by these NO2 groups. Now you don't even need 368 Kelvin temperature, you just need to warm this little and it will work, right? It will convert this weak nucleophile would easily be replaced by the strong electrophile, right? So we have observed, right? So presence of electron withdrawing group, these are electron withdrawing groups. Presence of electron withdrawing group increases the nucleophilic reactivity of nucleophiles, right? Or presence of electron withdrawing group increases the reactivity of these haloarenes. Now basically what is happening is the reactivity of this CCl bond is increasing due to the presence of electron withdrawing groups, right? What could be the reason? Since these are electron withdrawing groups, they will withdraw electrons, right, away from the benzene ring. These will withdraw electrons away from the benzene ring towards them, right? Since we know that benzene is electron rich species, right? Benzene is electron rich species. This is electron rich, right? And your OH is also electron rich. Earlier, in the absence of these groups, right, in this case, when OH will approach this benzene nucleus to replace this weak nucleophile, since this benzene is electron rich and your nucleophile is also electron rich, so this attack is difficult because electron rich species will repel one another. Now what we have done is we put these electron withdrawing groups at ortho and para positions. These electron withdrawing groups will withdraw electron density of this benzene ring, making it less negative, right? Now since this is less negative, so approach of this nucleophile would be facilitated, right? So now since this benzene nucleus has become less negative due to the presence of electron withdrawing group at ortho and para positions, right? Now this nucleophile would easily be able to attack this benzene ring, right? Thereby replacing this weak nucleophile easily compared to in chlorobenzene where you don't have any electron withdrawing groups, right? I hope this is clear. So basically what these electron withdrawing groups are doing, these electron withdrawing groups are decreasing the electron density of benzene ring, right, making it less negative. So now since this is less negative compared to this compound, the approach of this nucleophile would be easier, right, because now there would be less repulsion between electron rich and electron rich. Now this is less electron rich, so this approach of this nucleophile would be easier, right, on this benzene nucleus to replace this weak nucleophile. So nucleophilic substitution reaction in such compounds where you have electron withdrawing groups at ortho and para positions would be easier, right? We would be looking into this in little more detail in another video lecture, right? So I hope till this point it is clear, right? So basically from this video lecture, now what we have learnt is that haloarene is less reactive, right, towards nucleophilic substitution compared to haloalkanes, but presence of electron withdrawing groups, right, will increase the reactivity of haloarenes towards nucleophilic substitution. Why? Because electron withdrawing groups will decrease electron density on benzene nucleus, making it less negative, right? Now the approach of negative nucleophile would be easier, right? There would be less repulsion, so a stronger nucleophile would easily be able to approach the benzene nucleus in order to replace this nucleophile, right? I hope this is clear. Thanks.